Dear students, today we are going to discuss the concept, the derivatives of parametric functions from the topic differentiation. So let us begin. We will begin with one theorem related to parametric functions. So see here, if x is equal to f of t and y is equal to g of t are differentiable functions of t. Now see here, what is the meaning of parametric function? Here x is a function which is x is equal to f of t, means x depends on t, and y is a function which is y is equal to g of t and y depends on t. So x is equal to f of t and y is equal to g of t are called as parametric functions, where t is a parameter. And what is given here, x and y both are differentiable functions of t. So derivative of x with respect to t exists. Similarly, derivative of y with respect to t also exists, such that y is defined function of x. Now if y is defined function of x, then if you want dy by dx, then how will you get dy by dx? Dy by dx is equal to dy by dt upon dx by dt, where dx by dt is not equal to 0. So to get the derivative of parametric function, means if you want derivative of y with respect to x, then we have to use this rule. Now we will prove this theorem. This is very important theorem from exam point of view. So let us begin. We will use the Leibniz notations here. So for that, consider or let delta t be the increment in t, and let delta x, delta y be the increments in x and y respectively. Earlier in last lecture, we have discussed about Leibniz notations and first principle of derivative and the Leibniz notations that we have discussed. So related to that, we consider delta t as the increment in t and delta x, delta y are the increments in x and y respectively. Okay. Now we will consider the ratio. Consider the ratio delta y upon delta x is equal to delta y upon delta t into delta t upon delta x. So the proof starts with this ratio. So consider this. Now that gives, we get delta y upon delta x is equal to delta y upon delta t upon delta x upon delta t. So just this is the adjustment, or this is the consideration to which is very useful to get the proof of this theorem. Now taking limit delta t tends to 0 on both sides. Now after this, take the limit delta t tends to 0 on both sides. It becomes, see the left hand side here, limit delta t tends to 0 delta y upon delta x is equal to, here take the separate limit to the numerator as well as to the denominator. Now if you see this is the first principle of the derivative, this is also first principle of the derivative, and this is also first principle of the derivative by the Leibniz notation. So this is very important. Now see here, denominator is delta t and limit is delta t tends to 0. Here also denominator is delta t and limit is delta t tends to 0. But here in this case, here the term is delta y upon delta x. Here denominator is delta x and limit is taken on delta t tends to 0, as we have taken the limit on both sides. Limit on both sides, that is delta t tends to 0. But as we know that as delta t tends to 0, that implies delta x also tends to 0. Why this is possible? Because x depends on t. So delta t is the small increment in t. So delta t tends to 0, it gives delta x also tends to 0. So we can rewrite this step as, means we can rewrite LHS as limit delta x tends to 0 delta y upon delta x is equal to right hand side as it is. that is limit delta t tends to 0 delta y upon delta t upon limit delta t tends to 0 delta x upon delta t. So say this is equation number 1, and this is very important equation. Now we will think about given condition. Now what is given here? First of all, it is given that x is equal to f of t is a differentiable function of t. So by first principle of the derivative and by Leibniz notation, we can say that limit delta t tends to 0 delta x upon delta t exists. In short, x is equal to f of t is differentiable function of t means what? The derivative exists, means dx by dt exists, and what is that? It is nothing but limit delta t tends to 0 delta x upon delta t exists. So it must be finite. So say it is dx by dt. So derivative of x with respect to t exists. Similarly, y is equal to g of t is also differentiable function of t. That means derivative of y with respect to t exists. Means by Leibniz notation, limit delta t tends to 0 delta y upon delta t exists and it is finite. So say it is dy by dt. Now equation number 1 becomes, now see here, so if you put the values here for this limit, we get limit delta x tends to 0 delta y upon delta x is equal to dy by dt upon dx by dt. Because of the existence of this limit as well as this limit, we can write dy by dt upon dx by dt. Now dy by dt is finite quantity, dx by dt is also finite quantity, and it is equal to limit delta x tends to 0 delta y upon delta x. So this limit also exists. We can say that this limit also exists and it is finite. So after this we can write, hence limit delta x tends to 0 delta y upon delta x also exists and it is finite. So hence we get, as we get the existence of this limit, say it is dy by dx, and hence we get dy by dx is equal to dy by dt upon dx by dt, where dx by dt is not equal to 0, and hence we get the differentiation, that is derivative of y with respect to x, it is equal to dy by dt upon dx by dt. So this is very important theorem from the exam point of view, which is related to derivatives of parametric functions. So let us see how to write this. Okay, so try to understand again and again and see the result here. Okay, now we will solve some examples, simple examples, to get actual idea about this theorem. So the question is, find dy by dx if two functions are given to you, x is equal to a into t square and another function is given y is equal to 2at. Here the parameter is t. See here, x is in terms of t and y is in terms of t. Parameter is t, that means a is constant here. Now how will you find out dy by dx? See here solution. First of all, given x is equal to at square and y is equal to 2at. Two functions are given to you. Now we will differentiate both the functions with respect to t. So we get here dx by dt. See, how will you get the derivative of at square? It is 2at. Remember, a is constant, derivative of t square is 2t. So you can write it as 2at. Then derivative of y with respect to t, we get 2a only, because derivative of t is 1. So just the answer is 2a. Now finally we require dy by dx. Now by that theorem we know that dy by dx is equal to dy by dt upon dx by dt. So simply we get dy by dx is equal to 2a upon 2at, and hence as an answer you can write it as dy by dx is equal to 1 upon t. Now in case of parametric functions derivative, whenever you want dy by dx, you will get the answer dy by dx in terms of parameter. Okay, after solving means after taking separate derivative of x, then separate derivative of y, and then finally using this result, we get dy by dx, which is in terms of t, because here t is a parameter. So dy by dx is equal to 1 upon t. Here the answer is 1 upon t. Okay, so you have to solve up to this step. Now we will see another example. Suppose x is equal to a into cot theta and y is equal to b cosec theta. Here theta is a parameter, so a and b are constants. Now see the solution. Here it is given that x is equal to a into cot theta and y is equal to b cosec theta. Now we will differentiate both with respect to theta. Now see the what is the derivative here. Derivative of x with respect to theta, that is equal to, now we know that derivative of cot theta is minus cosec square theta, hence we can write minus a cosec square theta. Similarly, derivative of y with respect to theta is equal to, now we know that derivative of cosec theta is minus cosec theta into cot theta, so b is constant, so we can write minus b cosec theta into cot theta. See the derivatives carefully. Okay, now next step, now we have dy by dx is equal to dy by d theta upon dx by d theta. So hence we get dy by dx is equal to minus b cosec theta into cot theta upon minus a cosec square theta. Now try to simplify this. We get dy by dx is equal to minus minus becomes plus, and 1 cosec theta will get cancelled, and hence we get b cot theta upon a cosec theta. Now see the answer, which is in terms of theta. Okay, because here theta is a parameter. So try to solve such questions, very simple questions related to derivatives of parametric functions. The theorem is very important from exam point of view. So try to write yourself. Okay, so this is very important part of this topic. Okay, now in next lecture we will solve more examples related to this concept. Okay, thank you.